ACS gas training controls or understanding controls. My name is Alan Hart, and in today's video I'm back at the National Gas Centre for Excellence. I'm back here with Michael, and Michael's going to go through controls. So one of the biggest issues that people have when they go do their ACS is, because we don't do controls that much these days, people struggle to understand them. So Michael's going to go through the controls in real detail. I have done videos in the past with controls, but today we're going to go into it in a bit more detail. So hopefully when you go do your renewal on your ACS, or if you're a new trainee and you're going to go do your ACS for the first time, then hopefully this video will help you. If you've got any questions, please put me comments below. And as always, if you could put them thumbs up, really appreciate that. And subscribe and all that good stuff. Without further ado, let's go to Michael.
Hi guys, really good video for you today. We've noticed in the centre that one of the main areas that guys struggle on when they come for ACS is the control section. I'm sure many of the guys who are watching this video will remember at some point being stuck in an ACS and looking at a control that you're not familiar with and thinking, what is this? How do I test it? What's it called? How does it work? So today what we're going to do is we're going to go through each control that you're likely to come across on your ACS. We're going to show you it, how it operates, how it works, what it's called, how you test it, and different faults associated with it. So yeah, let's go across to the board and we'll have a look and we'll check each control out in its own merit. So before we look at the controls board, it's really important that we understand some of the components associated with it. So first of all, we're going to be working with many controls that operate using thermocouples, thermostats, and that kind of thing. We're also going to be looking at FSDs. So thermostats are there to basically maintain temperature via one method or another. FSDs are there to close the supply of gas if the flame's extinguished for any reason whatsoever. Now, FSD is just a flame supervision device, and it's important to remember when we're testing these flame supervision devices that depending on the appliance that the flame supervision device is on, it has a set period of time that it must operate within for it to be deemed passed. So top of the tree, the longest allowance is for gas fires. Now we're talking ILFEs and LFEs. If you've got a decorative fuel effect fire, then a DFE, then it's reduced to 60 seconds, whereas every other fire is 180 seconds. After that, we've got cooker hot plates and griddles, which are 90 seconds. They have to operate within 90 seconds. After that, most appliances that we're concerned with are 60 seconds, apart from water heaters between 35 kilowatts and 70 kilowatts that are 45 seconds. And again, it's important to check manufacturer instructions because some manufacturers might specify different allowances for their appliances, in which case you go with MIs. So how are most flame supervision devices going to work? So a lot of them use thermocouples and thermoelectric valves. So whenever you see a thermocouple, you will have a thermoelectric valve, and this is a thermocouple. So all it is two dissimilar metals that when it's heated via either a pilot light or a burner, will create an electric current, and the electric current will travel down the coil and then to a thermoelectric valve, and it will hold the thermoelectric valve open used by energizing a magnet. In the same way, when the flame is extinguished for whatever reason, this will start to cool down and it will stop producing the electrical current. Now, at some point within our allowance for our FSD, the electric current will stop energizing the magnet and the valve will spring closed, stopping the flow of gas. So that's a thermocouple. We're going to see a lot of them on our controls board. Another thing we're going to see quite regularly on the controls board is a file. Now, this works on the basis of liquid expansion. So the idea is that when this file's heated, it's usually located above a heat source so that it's there to monitor the temperature within an oven or within a heat exchanger maybe. And once it's heated, there's a vapor inside it, and the vapor will expand and travel down this tube, the capillary tube, and it will always either open or close something. It's usually a set of bellows. However, in the case of an electric thermostat, it can be a micro switch. So it always opens and closes something. However, in most cases, it's either bellows, or in some cases, it can be a micro switch. And that's liquid expansion. It can be used as a thermostat, or it can also be used as a form of flame supervision device, in which case you've got a file monitoring the presence of a flame, and it'll close the main supply of gas if the flame's extinguished. So now you've got an idea what we're going to be looking at, thermocouples, files, and how they work. Let's look at the controls board. So the first control we're going to look at is a liquid expansion thermostat with thermoelectric FSD. So this is a more modern type of oven setup. And what we've got is a liquid expansion thermostat, which is the thermostat at the top of the oven, which monitors the temperature within the oven and adjusts the flow of gas to suit. And then we've got a thermoelectric valve, which is the FSD. So because it's a thermoelectric valve, we know we've got a thermocouple there. So we have a thermocouple, which when heats up, will keep the burner on at its full rate. We've got a file at the top of the oven, which when it heats up, will cause the vapor to expand down the capillary tube and close a set of bellows in the valve, which will then only allow a bypass through. So what we're going to do now is fire the control up, fire it up, and we're going to talk about it as it's actually happening. So now we're going to look at how, from start to finish, the operation of this control works. So the first thing we're going to do is we're going to turn the gas on, and we're going to ignite it using the piezo igniter. We can see now that the flame is present and it's on full rate. Once the thermocouple is now getting hot, the dissimilar metals are now creating an electric current, and I can now remove my hand from there, and because the magnet's energized, it's holding the valve open. Possible faults on the thermoelectric FSD side would be if you can't get the appliance to stay on, in which case there's an issue. The thermocouple might be broken, there might be a break in the circuit, it might not be making a connection properly with the magnet. So our oven's now lit, and now the temperature in the oven is getting hotter and hotter, and this liquid expansion thermostat, this file, is starting to heat up, and the vapour inside it is now starting to expand down the capillary tube, and once it's hot enough in the oven, it's going to close a set of bellows, which will then only allow a small amount of gas via the bypass to keep the flame lit. So once that then goes down to low flame by just a setting, you'll see it's now just gone down to its lowest setting. And now, because it's starting to get cool again, it's just starting to rise back up. At which point, if I turn the thermostat down even further, you'll see there's only a small amount of gas being allowed through via the bypass. And then eventually, once this cools down, the vapour contracts, and then the bellows open again, allowing the gas pressure to increase to the main burner. So, potential faults on this setup is that once the appliance reaches temperature, the flame goes out and it's extinguished. So if that happened, it would be because when the thermostat's got to temperature, because the oven's hot enough and the vapour has expanded and closed the bellows, if the flame goes out completely, it's because the little bypass that allows that little bit of gas through to keep the burner lit on low flame is blocked. So there's no way of gas getting to the burner, so the flame's extinguished. Now, the test that you can perform on this type of appliance is if you turn the gas off completely to it, you can then test the FSD. So we'll do that now. So we're going to wait for the thermocouple to get hot. That's on now, and what we're going to do is we're going to isolate the gas. Now what we're looking for is, because it's a cooker, we allow 60 seconds for the thermoelectric valve to click and close the valve. There, it's just clicked. So as long as that happened within 60 seconds, that flame supervision device is fine. Now what we should also do is carry out what we call a mini tightness test. And that's the same when we test all flame supervision devices. Once they've operated, we don't close them. We carry out a small, we call it a mini tightness test. So you can do that via the meter, or you can do it if there's a test point on the on the appliance side of an isolator. You can do it there too. And all you're doing is you just take the gas pressure, close the valve so that it's not being replenished. And if the valve was passing still, you would see a drop on a manometer. So there we go, that's your liquid expansion thermostat with thermoelectric valve. So the next control we're going to look at is, again, a liquid expansion thermostat, but this time it's in conjunction with a liquid expansion FSD. Now, that might seem a bit confusing considering what we just looked at previously. But all this means is that as well as using a file at the top of the oven to monitor the temperature, we're also using another file in the flame, in the pilot light, to monitor the presence of the flame. Now this one works slightly differently, and it tends to be on older type ovens. Basically how it works is we fire the appliance up and the appliance lights on a low light, a small flame if you like. Now once that FSD thermoelectric, once the liquid expansion FSD gets hot, once that file starts getting hot, the liquid expands, or the vapor expands down the capillary tube, but instead of closing a set of bellows, this time it opens a set of bellows. So if you imagine you've got your burner with a small file inside it, the bellows in the FSD are closed, and once the file gets hot, the vapor expands and opens the bellows, allowing a full rate of gas through. Initially it's just going through a bypass, another bypass inside the FSD. We've also got, exactly the same way as we did before, another file which is located here in the top of the oven, exactly the same way as the one before. Now once the oven gets hot, the vapor inside that file expands and closes a set of bellows, again allowing a small amount of gas through a bypass to maintain the flame. So let's light this appliance up and see how it goes. So now we're about to turn on our liquid expansion thermostat with liquid expansion FSD. Now it's important to remember this is on an older type cooker, older type appliance. So we turn it on, we light our piezo. Straight away it's a really low flame, and that's because we're only allowing a little bit of gas through the bypass on the FSD. And once the file gets hot in the FSD, it will then open the bellows and allow full rate through to the burner. Now that normally takes anywhere between sort of 10 and 20 seconds depending on how old the appliance is, how old the controls are. So in any time soon now, we'll get a full rate through to our burner. It's important to note as well that this is the FSD side, that's the full burner. In here we've got our thermostat. So in here we've got another set of bellows that is fully open until the temperature in our oven gets hot enough for this file to then heat up. The liquid expansion will carry on through this capillary tube, and then it'll close the set of bellows here, allowing a bypass through, maintaining the flame there. So now we've got a full rate through our flame, through to our burner. Allow it to get hot enough, and eventually what we should start seeing once the oven gets the temperature is the flame just dipping, because it's trying to maintain that temperature within the oven. And then once it cools down, the flame will increase again to the burner. Now there's 3 possible faults associated with this type of appliance. So if you're ever called out to one of these older type cookers with a liquid expansion FSD as well as a liquid expansion thermostat, the 3 things we need to be aware of. First fault is you can't light the oven, it just won't light. If that's the case, it means that the bypass in the FSD is blocked, so you're not getting any gas through to the burner, even on to light on a low flame. Now, if that's the case, you'd identify that by not being able to light the oven. The other situation would be is if the oven gets the temperature, and once it gets the temperature, the flame goes out. If that's the case, it's because the bypass in the thermostat side, which is in this front section, that might be blocked. So when the bellows close on the thermostat side, there's no gas being able to go through the bypass to maintain the flame, so the flame just goes out completely. The third fault that you might get is if the customer is constantly complaining that they're burning food. Regardless of what they do, what setting they have the oven on, they're always burning food. Now what that will be is if the file or the capillary tube or the thermostat, it might be split, it might be broken, basically that vapour might have escaped, and when it's getting to temperature, it's not closing the bellows at all, so the oven's constantly on its highest rate and burning food regardless of what setting you've got it set on. So that is our liquid expansion thermostat with liquid expansion FSD. I'm just altering the setting there and it's gone down to low rate, and then eventually it'll creep back up when the thermostat at the top of the oven gets cool again. Cooker safety shut-off valve, or SSOV, safety shut-off device. Now these devices are typically on cookers. They tend to be more modern cookers, however some older models will have them on as well. So how does it work? Ultimately, it's a really simplistic mechanical device. The cooker lid, when it closes, will shut off the gas supply to the cooker, or to the hob, sorry. This is why on a gas tightness test we have to have them in the up position so that you're testing the full appliance. But the idea is that when you put the lid down, the closable lid, the gas supply can't be present, so that you can't have heat emitting onto the drop down lid. So how the device works is a simple plunger on a lever. So we'll just get the thermocouple hot so it stays on. And as we close the lid, you'll notice that there's a mechanical lever that as we close it, it pulls away and kills the gas supply through to the hob, if you like. And when we lift it back up again, the gas is present. But because the thermocouple's not being heated anymore, within 90 seconds for a hob, the gas supply is cut off. So that is your cooker safety shut-off valve. Really simple control, really basic control. If when you close the lid it didn't kill the gas supply and there was a safety shut-off valve on the cooker, then we would be looking at perhaps a disconnected lever, or an issue with the plunger. Maybe it's stuck, it's not lifting up to allow the gas supply through. If you come across it on an appliance, if the appliance has got a safety shut-off valve and it's just not working up properly, then that would be classified as ID. It's a non-functional safety device. Some older models do have drop-down lids, but they haven't got the device on them, in which case it would have been classed as not to current standards. So yeah, cooker safety shut-off valve, that's that. Thermoelectric valve with interrupter, or interruptible thermoelectric valve. We've already spoken about thermoelectric valves and how they work. You'll have a thermocouple, which is then engulfed by a flame or a pilot light. That will then heat up and create a small current or a small voltage that will then hold open a magnetic valve. So when we manually make the valve first, we manually open it, and then once the thermocouple is heated up sufficiently, it will then, the voltage and the current that it produces will hold the valve open via a magnet. Now, what we haven't discussed is how we can introduce interrupters into that. So types of interrupter could be thermostats, like overheat stats, or commonly in boilers we'll see high limit stats or overheat stats. On older single point water heaters, these were quite common. We had the interrupter wired into the thermoelectric valve. So let's look at one in operation. Just as before, the same setup that we used on our safety shut-off valve. We're now allowing the thermocouple to heat up. Once the thermocouple's hot, we can then let go of the valve. The magnet is now holding the valve open fully. What we've also got is the current and the voltage will travel is holding this valve open, but you can see we've got an interrupter wired in. That interrupter basically is wired to an overheat stat. So the current and the voltage is travelling through the tube, goes back through the overheat stat, and then back to the magnet, which is holding it open. If for whatever reason the overheat stat was to break, or it was to break its contact, the flame would go out. Because the thermocouple is still hot, if I press that in now, I've made the magnet again, and we can hear we've got gas again at the burner. So all that's happening here is we've introduced a break in the system, but that break is controlled via some form of thermostat or some form of device that is breakable. You may notice that we've got the overheat stat bridged out on this. That's because this overheat stat is faulty, it's actually tripped. So all we've done is we've manually overridden it by putting the connections on the same spade. So for example, this is something you might want to look at if you go out and you see boilers in the field. You could notice that somebody's bridged it out, in which case that would be another ID situation, because it's a safety device that's been manually bridged or overridden by somebody. So it's also RIDDOR reportable. So yeah, that's the interruptible thermoelectric valve. On this section of the video, we're going to look at two controls in their own merit. The first control is a solenoid valve. The second control will be a low pressure regulator, similar to what you find on most domestic gas meters that we deal with. This small valve here with the black actuator on top is a solenoid valve. And what a solenoid valve does is it's a valve that again utilises electricity and a magnet. So when we introduce electricity, the magnet energises and it draws the valve up and opens it. So I turn it on now, you'll hear that. Now we've got gas through this solenoid valve. We've also got a low pressure regulator. Now, a low pressure regulator, although this one looks slightly different, it's exactly the same type of regulator that you see on your gas meters. All the regulator does, or a governor, is it maintains a constant outlet pressure on a gas valve, and it does this via a diaphragm. So when the gas goes through the valve, depending on what the outlet pressure is, or what the system is drawn off from the regulator, the diaphragm will alter to maintain a constant outlet pressure. On a typical gas meter in a property, that outlet pressure will be 21 millibar plus or minus 2. On this low pressure regulator, for example, it's around about 6 to 10 millibar, depending on how we set it. You can adjust it. So if I allow gas through, light the burner, again we've got a thermocouple there that's heating up. Once that heats up to a sufficient temperature and produces enough current, it will then hold this valve open. Now, how can we test these two controls? Well, the solenoid valve is really straightforward. All you can do is turn the gas off, turn the electricity supply off to it. That's closed the valve, because what's happened is we've cut the electricity out, the magnet has lost its charge, and it's slammed shut. Turn it back on. The low pressure regulator, the way to think of it is you treat it exactly the same way as you would on a gas meter. We've got a test point that we can connect the manometer to, and all we want to make sure is that we've got the relevant outlet pressure, or the relevant pressure that we would expect to get from this regulator. If we haven't, again, we've got the adjustment point on top of the regulator where we can use a flathead screwdriver and we can change the outlet pressure. We can adjust the setting of the spring, which will then apply more or less force on the diaphragm, so that we can alter that outlet pressure. So how we would test it is we would take a working pressure after the outlet of the regulator. So there we have two controls in their own merit: low pressure regulator and a solenoid valve. The next controls we're going to look at work together. and we see them quite frequently on back boilers, or well, less frequently, but when you see a back boiler, generally you've got these two controls working together now. We've got an electric thermostat, which is housed in this black section here, in this black box, and we've also got a multifunctional control valve. Now let's talk about the multifunctional control valve first. A multifunctional control valve is called a multifunctional control valve because it does multiple functions. It incorporates three main components. The three main components are a regulator, which it uses to operate the outlet pressure. That's because it's range rated. We can generally set these appliances to give different outlet, we can set this valve to give different outlet pressures depending on what we want to range rate the appliance to. As well as a regulator, it's also got a thermoelectric valve which we use to light the appliance. We've got a pilot light here with a thermocouple, and we've got a manual valve that we push in that will become energized when the pilot provides enough, the thermocouple provides enough current. It also incorporates a solenoid valve. So the solenoid valve is in this section here, and it's when the electric thermostat, which we'll talk about in a minute, allows electricity through, it will energize the solenoid valve and allow gas through to the main burner. So again, multifunctional control valve, three main components. It's got a regulator, it's got a thermoelectric valve, and it's also got a solenoid valve. So we can see here our pilot's lit. It's already lit, so we've got our thermoelectric valve is energized. The valve's held open so that we're getting gas through to the pilot. The regulator we don't need to go into because we're not going to range rate it. However, if we now set the thermostat on the electric thermostat side to allow enough electricity through, we'll see our back boiler unit then lights. It allows gas through to the main burner by opening up the solenoid valve. Now, how an electric thermostat works is we're used to talking about files in liquid expansion terms, but not all files open and close bellows. Some of them open and close micro switches, which is the case with our electric thermostat. So our file here is now heating up, and when it gets to a certain temperature and the vapor expands far enough, it will open and close a micro switch, a little tiny electrical switch. Now that's all it'll do all day long, as this unit's operating. It'll just heat up, close the micro switch, cool down, open the micro switch, and we'll get this constant cycling of the appliance. And that's how it works pretty much. So all you'll see is, once it gets the temperature, you'll see it'll turn off, and then once it gets cool again, it'll come back on, and it'll just do that and maintain the temperature that we want in the property throughout the day. The other control that we do have on this, one thing that we do need to note, is that we've got what we call an ODS, an oxygen depletion sensor. Now, an oxygen depletion sensor on this unit, it takes its air for combustion for the pilot light from above the unit, above the heat exchanger. So the idea is if the air above the heat exchanger was vitiated or depleted in oxygen for whatever reason, it would then turn off. It would make the pilot light go vitiated, and then the thermocouple will cool down. And that's what it's meant to do. So if you actually were servicing this appliance and you were testing the oxygen depletion sensor, you would put your finger over that and you would expect the pilot light to go yellow and orange. So you're taking its air for combustion away from the pilot light. When you do that, it should go yellow. That's what you want it to do. If for whatever reason you do that and it stays blue, that would indicate that there's a break in it somewhere. The pilot light's getting its air for combustion from somewhere else. In which case, if the air above the burner was vitiated because, wrongly it wasn't meant to be vitiated, whereas this would not, it's the job of the ODS to pick it up. It's not doing that. And again, that's a safety device that's non-operable, so that would be ID as well. So yeah, we've looked at multifunctional control valve, electric thermostat, and we've just looked at an ODS as well, oxygen depletion sensor, which is pretty much the same as an atmospheric sensing device. That's it for that one. The next two controls we're going to look at, again, work in conjunction with each other. we've got an air gas ratio valve or zero governor, and we also have flame rectification. So this is our air gas ratio valve, otherwise known as zero governor. The reason it's called a zero governor is because the fan draws the gas through the unit, so it sucks the gas, creating a negative pressure. So if you were to try, even attempt to try and take a burner pressure, the reading you would get would be less than zero. It'd be a negative pressure you'd get. So how it works is the fan kicks in and draws both gas and air in at a predetermined ratio and mixes it before it gets to the burner point. Once it gets to the burner point, then we move over to the flame rectification side. We've done a video on flame rectification before. If you guys want to go and have a look at it, you can. However, to try and keep it as simple as possible, our circuit board or PCB sends power is constantly sending a voltage to the flame rectification probe, which is located just behind this section here. Now that voltage, all it wants to try and do is get back to the board. But the only way it can do that is by traveling through a flame. So when the board sends power to the fan and the gas valve and the ignition probes to create a flame, once that flame's present, the voltage that's on the rectification probe then travels through the flame, and in going through the flame it converts from AC to DC current. It travels back via an earth or a ground lead, and once it gets back to the board as DC current, the board knows that there's a flame there. So it happens pretty instantly. When we turn it on now, you'll see the fan kicks in. You'll see now that the gas will come through, the ignition probes will start sparking, and then pretty instantly, as soon as the flame there, stops arcing and the board gets a burner light on it. So in the same vein, if I was to disconnect the probe on the ignition probe, on the rectification probe, I've taken that current away from the board. Now there's no way of the current getting back to the board. So when the burner lights, the board doesn't receive DC current. So what will happen is it'll light, but it'll still carry on trying to arc and ignite because the board doesn't know there's a flame there. So then it'll go through that sequence a number of times and then eventually go to lockout. So if you do have any issues, it'll generally show up on a boiler as an ionization fault or ignition fault. If it is associated with the flame rectification side, generally it's a case of the board isn't receiving the current back. So it might be that there's a break in the rectification lead, it might be that there's a fault on the board, so it's not recognising the current DC current coming back. Or it could just be because there's a problem with the gas valve or the ignition probes and there's no flame being created, it's just gas being sucked and blown out the flue again. So that is flame rectification in a nutshell. The fan kicks in, draws gas through the air gas ratio valve, as well as air, premixes it, sends it to the burner. Once it gets to the burner, it's ignited by the ignition probes. The voltage that's present at the rectification probe then converts from AC to DC by travelling through the flame and makes its way back to the board. Once the board senses that there's DC current there, it knows there's a flame there and stops trying to ignite and then moves on to the next part of the sequence, i.e. allowing more gas through to the main burner, or ramping up, whatever the next stage may be, as relevant to which boiler the zero governor's on. Really straightforward. I hope you guys have enjoyed this video. We've covered all the controls now. As always, if there's anything else that you guys would like us to do a video on, that would be, let us know. We'd be greatly appreciated. We appreciate the feedback, and we'd happily do anything that you guys want us to do. Or as always, like and subscribe as well. I know that these videos help a lot of people, so any support you can give us would be great. Thanks, guys.
Thank you very much for that, Michael. And once again, thank you to the National Gas Centre for Excellence. Hope you've enjoyed this video. If you've got any questions, if you've got any requests, please put them in the comments below and we'll try as best wherever possible to do what we can. One thing I will point out is always read the installation instructions, always read any manuals that are up to date at the time. Sometimes these videos, they can age and not always age well. So it's just worth checking any current documents at the time. Thanks for watching.